Greetings everyone, Enox here. So today we're going to learn macOS shellcoding on x86 architecture. Let's begin. In this video, I'll be covering x64 assembly refresher, which is the prerequisite for this video. So if you're not familiar with assembly, I would highly recommend learning it and then revisiting this video at a later stage. Next, I'll cover what are system calls, and then lastly, we'll be creating a reverse shell using x64 assembly. Let's start with x64 assembly refresher. What is assembly language? In simple terms, you could say it's a low-level programming language used to communicate with computer hardware. And each assembly instruction corresponds to a specific machine instruction executed by the CPU. For example, on the right we have a figure which shows assembly instructions used to invoke execve function, which executes sh. Next we have x64 bit registers. So first we have general purpose registers, which are used for arithmetic operations and data movement. Next we have index registers, which are usually used for string operations. After that we have RSP, being the stack pointer, which points to the top of the stack. After that we have RBP, which is the base point register, which is used to reference parameters and local variables on the stack. And then we have a few additional general purpose registers ranging from R8 to R15. And lastly, we have instruction pointer RIP, which holds the address of the next instruction to be executed. On the right, we have a figure which shows function arguments and return value registers. So basically, if we were to execute a function in assembly, the arguments are to be stored in the following order. That the first argument is to be stored in RDI register, second argument in RSI, and so on. And then the return value of the function, if it has two return value, the first one will be stored in RAX and the second one will be stored in RDX. Next we have x86 instructions. So the first one being data movement. So move, which stands for MOV, is used for moving values into different registers. Push is used to push data onto the stack. And then pop is usually used to move a value from the stack into a certain registers. And LEA, which loads effective address, is used to load the address of a memory location into a register. Next, we have arithmetic instructions being addition, subtraction, multiplication, division, increment, and decrement. These are self-explanatory, so I won't be covering them. Next, we have logic instructions, which are AND, OR, XOR, NOT, and CMP being comparison. And lastly, we have control flow instructions being jump, which is an unconditional jump to a specified address. And then we have JNE, which stands for jump if not equal, which is a conditional jump. And then we have call, which calls a procedure or function. And finally, RET, return from a procedure. Let's proceed to system calls, or for short, syscalls. So what are syscalls? So system calls are interfaces provided by the operating system for user-level programs to request services from the kernel. So you could say it acts as a middleman between user-level programs and the kernel. And these apps use syscalls to access services like file operations, memory and process management, and a lot more. And each function system call has a number which should be stored into RAX register before invoking syscall instruction. In figure 3, we have syscall numbers for various functions, which are retrieved from the syscalls.master file from XNU source code. Also, please note that these system call numbers are for BSD type calls. So we need to add the system call number to the following hexadecimal string represented in this slide. Next, we'll be writing assembly instruction for the following C code, which basically invokes write function, which writes hello to the output and then exits with the code 0. The syscall number for these functions are represented here, for write being 4 and for exit being 1. Let's begin with the write function. We can see that this function takes 3 arguments. So the first step would be to place write syscall number in RAX using the following instruction: move RAX, 0x to 000004. And the step 2 is storing the first argument, which is 1, into RDI using the following instruction: move RDI, 1. Step 3 is storing the second argument, which is our string hello, into RSI register, which is done using these 3 instructions. So let me break these instructions down. So first we have move RBX, hello. So what this does is this stores hello into RBX register. Next we have push rbx. This pushes the string onto the stack, which is rsp. After that, we do move rsi, rsp. Now what this does, it stores the address of the hello string on the stack into rsi register. Now step 4 is storing the third argument being 5, which is the length of our string hello, which is done using the following instruction, move rdx, 5. Step 5 being invoking the syscall using syscall instruction. And the completed instructions for write function invocation looks as follows. Let's proceed on to the exit function. It takes one argument. So the first step is placing the exit syscall number in rax, which is done using move rax, and the hexadecimal value. After that, our step 2 will be storing the first argument, that is 0, into rdi using the following instruction, move rdi, 0. Step 3 would be to invoke the syscall using syscall instruction. And the completed instruction for exit function looks as follows. And testing our code on our Mac, we are able to compile it and execute it fine. As seen in the screenshot, the output hello is displayed and the program exits. Although there's a major issue here. So we have to tackle null bytes while performing the syscall. Now where are these null bytes and how? And they can be problematic to us when inserting shellcode into certain applications, as they don't handle them well. So we observe that when storing the syscall number, we encounter two null bytes. As seen in figure 5, when storing the syscall number for write function, there are two null bytes, and when storing syscall number for exit function. We also see there are other null bytes, but for the sake of this example, we will not address this issue. But don't worry, while writing the reverse shell, we won't be having any null bytes, so we'll make sure of that. So how will we tackle these null bytes? We will utilize the bts instruction, which basically sets the nth bit in a bit string to 1 to store the syscall number on the stack. Now let's see its magic using bts to tackle null byte. So step 1 is pushing 4 on the stack and pop using to store it into rax register, 4 being the syscall number. So it is done using the following instructions. Push 4 pushes it onto stack, pop rax moves that value into rax. So following is the binary representation of the number 4. Now the step 2 would be to set the 25th bit to 1 using bts, and this is done using the following instruction, bts, the register name rax, 25, which is the 25th bit. Now this is what happens here. So as you see that the value on the 25th bit was set to 0, it became 1. And now this binary translates to our syscall number. Now if we were to compile this and run this and also dump the shellcode for it, we see that there are no longer any null bytes when storing the syscall number. Let's proceed on to creating reverse shell in x64 assembly. So following is a figure showing reverse shell C code, which we will be writing into assembly. So what this code usually does is it sends a reverse shell on port 444 to this following IP address, and it executes bin zsh. Let's begin with the socket function. So there's one interesting thing. We see that it is using afinet as the first argument and sockstream as the second argument. We have no idea what values do we have to push onto the stack or into the registers. So first let's check the documentation for the socket function. So we see that these values will probably be defined in the socket.h header file. So let's find that out from the xnu source code, which is available on macOS GitHub. So we see that the values, the integers that represent these, are as follows. For sockstream 1, for afinet it's 2. Now let's proceed to place these values into registers. So step 2 will be to placing afinet, which is 2, into RDI register, which is done using push 0x2 pop RDI instruction, and we see the value of RDI updated. The next step would be to place sockstream, which is the value 1, into RSI register, which is done using these instruction push 0x1 pop RSI, and the RSI register is updated as follows. And then we have step 4, which is placing null, which is 0, into RDX register, which is done using XOR RDX, RDX. Now, how is this becoming null? That's the question. So basically, when you perform XOR operation on the same values, so here as we see we are performing it on RDX and RDX, these being the same, the output becomes null. So that's how the value RDX becomes null here. Then step 5 is placing syscall number for socket, which is 97, and invoking the syscall, which is done using push 97 pop RAX BTS RAX, 25, and then invoking it using syscall. We previously discussed this method in the syscall section. Step 6 being saving the return value from the syscall RAX in R9. We are doing this because, as seen here, the socket, the return value from this is stored into an integer socket. So we'll be saving the output from this function RAX register into R9 for later usage. And as seen, there are no null bytes in the invocation of socket function. Now let's proceed on to the following code. So we see that a struct is being used, and then we have syn family being AFINet. We already know this value. Then we have syn port being the port 4444, and then we have the IP address being stored in synadder.sadder, which is 172.16.128.208. Now checking the source code for socket.h header file, we see the following structure. So the main structure being sockadder in, we see that it has synlen, which we see that we haven't used here, so which will be left null. Then we have syn family, which is AFINet. Then we have syn port being 44444, and then we have synadder being the address or the IP address, and then we have syn 0 of 8 bytes long. So this is interesting. We haven't used this either. So basically we have 8 null bytes, you could say that. So syn 0 will be basically stored as follows, which is null, and it is of 8 bytes. And then how would we store the IP? So we perform an operation of converting the IP, which is this, to hex. It becomes 0xAC1080D0. So now synadder is of 4 bytes, which is 0xAC1080D0. Then we have syn port, which is 4444, and the hex representation is 0x115C, and it is of 2 bytes. Then we have syn family being 0x02 for AFINet, which is of 1 byte, and synlen, which we haven't used, which will remain null, so it will be of 1 byte. So basically RSI, which is the second argument, must store the following value, which is 0x followed by around 16 zeros, and then D0 8010 AC 5C 110200. So if you notice that we have reversed synadder and syn port in the value we're storing into RSI, this is to ensure compatibility and proper interpretation of networking related data. We reverse the byte order to follow the big Indian format, which is the standard convention used in networking protocols. Let's proceed on to the invocation of connect function. So step 1 is RDI, storing the argument, which is soct, being which we previously stored in R9. So we basically do move RDI, R9. Then step 2.1. So we'll do this in sections because RSP, the syn 0 itself is of 8 bytes, and then we have 8 more bytes to be stored. So this is done as follows. So XOR RSI, this makes RSI null, and then push RSI. So this basically pushes this onto the stack, and then we'll push this value, which is our synadder, syn port, syn family, and synlen. So rather than pushing this value, if we were to move this value, which contains 00, which is a null byte, we'll add it 1 here. Now we are doing this to avoid null bytes. So once we've pushed this value, and then we use DEC RSI, which is used for decrementing it by 1. So this address basically becomes this, as shown here. To avoid null byte, we push and decrement it by 1. And then we use push RSI to push it onto the stack. And then finally we push the entire value being 0x, 16 zeros and so on onto the stack, and then pop it into RSI register. And then step 3 being the third argument, which is 0x10, which is size of 16 bytes, and this size is basically of our struct which we previously stored in RSI. This is done using push 0x10 pop rdx. Step 4 is placing syscall number for socket for connect, which is 98, and invoking the syscall, which is done using the following instructions. And now we have null byte free connect shellcode as seen in the screenshot provided. Now the third part is dup2 function being executed, or dup2, which basically executes 3 times as seen in. We observe that 3 invocations of dup2 with the second argument varying from 0 to 2. So rather than invoking this syscall and updating the arguments, the second argument value again and again, we will do a loop using JNS instruction, which stands for jump if not signed, for invoking dup2 thrice. So what does this function usually do? So if RSI is not negative, the jump will be taken back to the dup2 loop label. This will repeat the process of invoking dup2 with the decremented value of RSI until RSI becomes negative. I know right now this doesn't seem to make sense to you because you have no idea like how is this really happening. Don't worry, in the next slide we will show like how this actually happens. So this is the assembly code. So here we see that move RDI, R9. This basically stores the socket which we saved previously into RDI being the first argument. Then we push 2 into RSI, so the second argument becomes 2, and then pop it into RSI. Then we have dup2 loop section. So here we push the syscall number for dup2, which is 90, pop it into RAX and perform the BTS function and invoke the syscall. And then we decrement RSI by 1. So basically initially it was 2, it becomes 1, and then JNS dup2 loop. So this basically checks if RSI is greater than equals to 0. So in the first loop it is obviously greater than 0, so it jumps back to dup2 loop. So rather than explaining like this, let's go to the execution flow of dup2 loop. So the first is the move RDI, R9, and then it is popped into RSI. RSI becomes the following. And then the syscall is invoked, which invokes the following function. And then if we see RSI is decremented, it becomes 001. And then it checks whether RSI is greater than or equal to 0, and it is not, so it should jump back. And it jumps back to the stop of dup2 loop. It performs the syscall again, it becomes dup2 soct1. It decrements it again, it becoming 0. It performs the check again, and it will jump back again. And then perform the syscall again. It becomes dup2 socket 0. Now if we decrement it again, it becomes -1. Now JNS is unable to, value stored in RSI becomes negative, which is less than 0. So it does not jump back again. It then moves to red, the next instruction. Next, let's move on to execve function. So here we see that it takes 3 arguments, but the first argument being /bin/zsh, second one being argv, which is an array, and then we have null. So step 1, which is rdx, will be storing rdx. We'll just do XOR rdx instruction, which makes rdx null. Then step 2, which is the first argument will be stored. So when storing /bin/zsh string, we have to make sure that it is null byte terminated, otherwise it's going to cause issues. So this is done using the following instructions. First one being push rdx, which pushes the value we basically made null, so it pushes null this onto the stack, and then it does move rbx, /bin/zsh. This stores /zsh into rbx. This is then pushed onto the stack, and then this value from the stack is the address to this value on the stack is stored into RDI. So this is the following process. To explain it once again if you are confused. So push rdx, this basically pushes the null onto the stack, and then moving the rbx bin zsh and pushing this value onto the stack. The stack looks like this. So this is our /bin/zsh, and it is null byte terminated. Next we move on to the step 3, which is storing argv into RSI. register. So we'll basically be storing null and slash bin zsh null byte terminated. So first we'll store the null, which is done using push rdx, which stores null, and then we store push rdi, which stores the null byte terminated slash bin slash zsh string onto the stack, and then we move this value into rsi, which is the third argument register. So this is another explanation. So this is the argv1 to make more sense. This is null, and argv0 being slash bin slash zsh null byte terminated, which we had stored in step 2. And then finally we'll invoke the syscall to execve function using the following instruction, push 59 being the syscall number for execve function, and then we pop it into rax, change the 25th bit, and invoke the syscall. And we see that this is even null byte free. There are no null bytes here. Let's test our reverse shell. So we are able to compile and execute it without any issues, and we receive a shellcode on that machine as the user enox. Furthermore, if we perform hooking and checking what functions are being invoked, we see that first socket is executed, then connect, then dub2, and then finally execve. You can find the entire shellcode on my GitHub on OS X exploitation GitHub repo. Thank you for watching. I hope you've enjoyed and learned a lot. If you have any questions, feel free to reach out to me on Twitter or on Discord. I wish you all good luck. See ya.